In this video, we'll explore the reactions and versatility of alkenes in organic chemistry. We'll begin with a review of the fundamental properties of alkenes, followed by a discussion on how the pi electrons in alkenes function as nucleophiles in various reactions. Then we'll dive into a detailed exploration of key alkene reactions, covering their key reactive partners, mechanisms, reagents, and synthetic products. Let's begin the video with a review of alkenes. Alkenes are hydrocarbons characterized by at least one carbon-carbon double bond consisting of a sigma bond sp2 orbital overlap and a weaker pi bond, sideways p orbital overlap. This weaker pi bond makes alkenes more reactive than alkanes. The double bond has a planar geometry with bond angles around 120 degrees, and restricted rotation leads to cis-trans isomerism in di-substituted alkenes. According to Zaitsev's rule, alkene stability increases with the degree of substitution, with tetrasubstituted alkenes being the most stable, followed by trisubstituted, disubstituted, monosubstituted, and unsubstituted alkenes in that order. We've previously learned how to synthesize alkenes during our discussion of elimination reactions, and we've also had a glimpse into their reactivity through radical reactions involving allylic radicals. Now let's begin our discussion of the important alkene reactions covered in this course. We'll start by identifying key reaction patterns commonly associated with alkenes and defining some essential terminology to make the concepts easier to follow as we move forward. Most of the reactions of alkenes we will cover fall under the category of addition reactions. In these reactions, the carbon-carbon pi bond is broken and replaced with two new carbon-carbon or carbon heteroatom sigma bonds, resulting in the formation of more saturated products. Below is a diagram of a generic alkene undergoing an addition reaction with the reagent XY. In this reaction, X and Y are added to the starting material, replacing the pi bond with new sigma bonds between carbon X and carbon Y on adjacent carbons. The added groups X and Y can either be identical or different, depending on the specific reagent and reaction conditions. As we progress through the video, we'll explore the various types of addition reactions and the different combinations of X and Y that can be added to alkenes. If the two new single bonds to carbon involve identical groups, the addition reaction will produce only one constitutional isomer. For example, if X2 is added to a double bond instead of XY, there is only one unique way to arrange these groups in the product. However, if the alkene reacts with a reagent like XY, forming two different bonds to carbon, two constitutional isomers can result, provided the alkene is not symmetrical. This occurs because the groups X and Y can attach to the two carbons of the former double bond in different orders, creating distinct connectivity. Because these constitutional isomers result from adding the two groups to different regions of the alkene, they are often referred to as regioisomers in the context of addition reactions. The tendency for one regioisomer to form preferentially over the other is known as regioselectivity. If an addition reaction lacked regioselectivity, we would expect a one-to-one mixture of constitutional isomers. However, as we'll soon see, many addition reactions exhibit predictable patterns of regioselectivity. The most common pattern we'll encounter is known as Markovnikov regioselectivity, named after the scientist Markovnikov, who first described this trend in alkene addition reactions. Markovnikov observed that in the addition of HX to alkenes, the CX bond, where X is the halogen, typically forms on the more substituted carbon of the alkene, while the CH bond forms on the less substituted carbon. This arrangement of bonds, where the CX bond is formed on the more substituted carbon and the CH bond on the less substituted carbon, results in a specific product he dubbed the Markovnikov product. The Markovnikov product is the constitutional isomer that arises when the more substituted carbon of the double bond becomes bonded to the electronegative group X, while the less substituted carbon becomes bonded to hydrogen. This product is considered the major product in reactions that follow Markovnikov's rule, due to the inherent regioselectivity of the reaction. In the opposite scenario, where the electronegative group X is added to the less substituted carbon and the hydrogen is added to the more substituted carbon as the major product, this is referred to as the anti-Markovnikov product. Ultimately, there are three possible patterns for regiochemistry that can be applied to all the addition reactions we will learn moving forward. The major product can exhibit Markovnikov regiochemistry, where the electronegative group is added to the more substituted carbon, anti-Markovnikov regiochemistry, where the electronegative group is added to the less substituted carbon, or no regiochemistry, when the two groups being added are identical, resulting in only one possible product, regardless of substitution patterns. Now that we've discussed regioselectivity, let's move on to stereoselectivity in alkene reactions. Because alkenes are planar in nature, addition reactions can form bonds on either face of the planar double bond. This means there are only two unique ways for the groups to be added: syn addition or anti-addition. In syn addition, the two groups are added to the same face of the alkene, resulting in a dihedral angle of 0 degrees between them. In anti-addition, the two groups are added to opposite faces of the alkene, creating a dihedral angle of 180 degrees. It's important to note that syn versus anti-addition refers specifically to the stereochemistry of how the groups are initially added to the double bond. In non-cyclic alkenes, the saturation of the double bond during the addition reaction allows free rotation around the newly formed single bonds, enabling the molecule to adopt different conformational isomers. For example, in the dihydroxylation of ethylene, the reaction initially forms a syn-vicinal diol due to the stereoselectivity of the addition. However, through bond rotation, the molecule can adopt a more stable conformation where the hydroxyl groups are anti to each other. This distinction becomes more apparent with ring-bound alkenes, where the rigidity of the ring prevents bond rotation. In these cases, the stereoselectivity of the addition reaction is maintained. For instance, in the dihydroxylation of a cycloalkene, the product retains the stereoselective syn-vicinal diol configuration, as the ring structure restricts conformational changes. Again, there are only three different patterns for stereoselectivity with addition reactions: reactions that give exclusively syn addition products, anti-addition products, or a roughly equal mixture of syn and anti-addition products. Stereoselective reactions are not to be confused with stereospecific reactions. Stereoselective reactions are said to be stereospecific when the stereochemistry of the starting materials completely determines the stereochemistry of the product. All stereospecific reactions are stereoselective, but not all stereoselective reactions are stereospecific. We will discuss whether the reactions we learn are stereoselective but not stereospecific, or both, as we progress further into the video. Now that we've covered the main terminology and patterns to watch for, we can move on to discussing our first new alkene addition reaction, the addition of HX. The addition of HX across a double bond involves breaking the CC pi bond and forming a carbon-halogen bond and a carbon-hydrogen bond. This reaction typically yields the Markovnikov product as the major product, where the halogen is added to the more substituted carbon atom of the alkene, and the hydrogen is added to the less substituted carbon. Importantly, this reaction is not stereoselective, meaning it produces a mixture of syn and anti-addition products, as the halogen and hydrogen can add to either face of the planar alkene. Let's discuss the reactive partners in this reaction and propose a mechanism for the addition reaction. In this reaction, the alkene's pi electrons serve as the nucleophile, attacking the acidic delta plus proton of the hydrohalic acid, HX, which acts as an electrophile. The mechanism begins with the protonation of the alkene, where the pi electrons attack the proton from HX, breaking the HX bond and forming a carbocation intermediate. The stability of this carbocation determines the regioselectivity of the reaction, with the more substituted carbocation favored due to the greater stability. In the next step, the halide ion, X-, acts as a nucleophile and attacks the carbocation, forming a new sigma bond and completing the reaction. The result is the Markovnikov product, where the halogen adds to the more substituted carbon of the alkene and the hydrogen to the less substituted carbon. This reaction is not stereoselective, meaning both syn and anti-addition products are typically formed. It's important to keep in mind that because this reaction proceeds through a carbocation intermediate, the carbocation can undergo rearrangement if a more stable carbocation can be formed. For example, if we replace the R group in this generic alkene with an isopropyl group, The initial formation of the carbocation intermediate during the protonation of the alkene will be followed by a rapid rearrangement to a tertiary carbocation, which is more stable. This rearrangement leads to the formation of a tertiary halide as the major product, rather than the Markovnikov addition product we might have initially predicted. The next reaction we will discuss follows a pattern similar to the addition of HX, the addition of water, also known as the hydration of alkenes using aqueous acid. This reaction results in the addition of a hydrogen atom and a hydroxyl group, H and OH, across the double bond, following Markovnikov regioselectivity. The hydration of an alkene, or the addition of H2O across a double bond, involves breaking the CC pi bond and forming a carbon hydroxyl bond and a carbon hydrogen bond. This reaction typically yields the Markovnikov product as the major product, where the hydroxyl group is added to the more substituted carbon atom of the alkene, and the hydrogen is added to the less substituted carbon. Importantly, this reaction is not stereoselective, meaning it produces a mixture of syn and anti-addition products, as the hydrogen and hydroxyl can add to either face of the planar alkene. In this reaction, the alkene's pi electrons serve as the nucleophile, attacking the positively charged proton of the aqueous acid, hydronium ion, which acts as the electrophile. The hydronium ion is formed by an acid-base reaction between water and a strong acid such as sulfuric acid or perchloric acid, which is used in catalytic amounts to produce hydronium and the conjugate base of the strong acid. The mechanism begins with the protonation of the alkene, where the pi electrons attack the proton from the hydronium ion, breaking the HO bond and forming a carbocation intermediate. The regioselectivity of the reaction is determined by the stability of the carbocation, with the more substituted carbocation being favored due to its greater stability through hyperconjugation and inductive effects. In the next step, water, being the only nucleophile present, attacks the carbocation, forming a new sigma bond and producing an oxonium ion intermediate. Finally, the oxonium ion is deprotonated by another water molecule in the solution, completing the reaction and yielding the Markovnikov alcohol, where the hydroxyl group is bonded to the more substituted carbon and the hydrogen to the less substituted carbon. It's important to keep in mind that because this reaction proceeds through a carbocation intermediate, the carbocation can undergo rearrangement if a more stable carbocation can be formed. For example, if we replace the R group in this generic alkene with an isopropyl group, the initial formation of a secondary carbocation intermediate during the protonation of the alkene will be followed by a rapid rearrangement to a tertiary carbocation, which is more stable. This rearrangement leads to the formation of a tertiary alcohol as the major product, rather than the Markovnikov alcohol we might have initially predicted. Notably, this reaction can also proceed when the aqueous acid is HX dissolved in water. In this case, the water, which acts as both the solvent and the nucleophile, will react with the carbocation intermediate rather than the halide ion, despite the halide being a much better nucleophile. This occurs because the concentration of water far exceeds the concentration of the halide ion, giving water a greater likelihood of reacting with the carbocation. As we've just discussed, the hydration of an alkene using aqueous acid can present challenges due to the possibility of carbocation rearrangements. To avoid these rearrangements, an alternative reaction can be used: oxymercuration demercuration. This reaction employs a different set of reagents and a distinct mechanism to hydrate alkenes while bypassing the formation of a free carbocation, thereby preventing rearrangements and ensuring a more predictable outcome. To synthesize a secondary alcohol from this alkene, we can employ the oxymercuration demercuration reaction. In the first step, the alkene is treated with mercury 2-acetate HgOAc2 in water and tetrahydrofuran, THF. This step facilitates the Markovnikov addition of a hydroxyl group to the more substituted carbon without forming a free carbocation intermediate, avoiding potential rearrangements. In the second step, the reaction mixture is treated with sodium borohydride NaBH4 and sodium hydroxide NaOH, which reduces the mercurial intermediate, replacing the mercury group with a hydrogen atom and yielding the secondary alcohol as the final product. In this reaction, THF is added to increase the miscibility of the alkene in water, ensuring that the reaction proceeds efficiently. Let's walk through the mechanism of this reaction to understand how it avoids the formation of a carbocation intermediate. In the first step of oxymercuration, mercury 2 acetate HgOAc2 undergoes heterolytic cleavage of one of its HgOAc bonds. This results in the formation of a mercury 2 cation and an acetate anion in equilibrium. The mercury in the cationic species is highly electrophilic and undergoes nucleophilic attack by the pi bond electrons of the alkene. This reaction forms a three-membered mercurinium ion intermediate, where single electron bonds are established between the mercury atom and the two carbons of the former double bond. This structure avoids the formation of a free carbocation ion, stabilizing the intermediate and preventing rearrangements. The mercurinium ion is then ring-opened by water, which acts as the nucleophile. Water attacks the more substituted carbon of the mercurinium ion, analogous to the mechanism of protonated epoxide ring opening. When water attacks, the single electron from the mercury-carbon bond at the attacked site is transferred to the mercury-carbon bond on the less substituted carbon, converting it into a two-electron bond. This leaves the mercury attached to the less substituted carbon. The resulting oxonium ion, formed by the addition of water, is then deprotonated by another water molecule in the solution, yielding the product with a hydroxyl group attached to the more substituted carbon, Markovnikov regiochemistry, and the mercurial group attached to the less substituted carbon. This completes the first step of the reaction, setting up the product for the demercuration step that follows. In the second step, sodium borohydride, NaBH4, which we've previously encountered as a reducing agent for carbonyl compounds, reduces the carbon-mercury bond to a carbon-hydrogen bond. The nucleophilic pair of bonding electrons in the boron hydride bond attacks the electrophilic mercury atom, breaking the mercury-carbon bond and transferring hydrogen to the carbon atom. This reaction also breaks the mercury acetate bond, resulting in the formation of intermediate species. Subsequently, the mercury atom excises itself from between the carbon-hydrogen bond, forming the final carbon-hydrogen sigma bond and releasing free mercury. This transformation can proceed via a free radical mechanism, though the details of this mechanism will not be elaborated on in this video. Ultimately, this second step, known as the demercuration step, removes the mercurial group from the product of the first step and yields the desired Markovnikov alcohol as the final product. The sodium hydroxide acts as a fail-safe to address a potential issue with nucleophilic competition during the reaction. If the concentration of water is relatively low, there could be competition between water and the acetate anion, which is generated during the heterolytic cleavage of the mercury acetate bond in the first step. Both species are nucleophilic and can participate in the mercurinium ion ring opening reaction. If the acetate anion performs the nucleophilic attack instead of water, the resulting product would be an ester rather than the desired alcohol. By introducing sodium hydroxide into the reaction, the hydroxide anion can react via basic hydrolysis of the ester to regenerate the desired alcohol product. This process is analogous to the hydrolysis step seen in the synthesis of a secondary alcohol from a secondary halide using an SN2 reaction. Importantly, this hydrolysis step does not interfere with the demercuration step, which proceeds unaffected. Instead, the sodium hydroxide acts as a fail-safe mechanism, ensuring that even if the acetate anion competes successfully in the ring opening step, the final product will still be the desired Markovnikov alcohol. This reaction is selective for the Markovnikov regiochemistry, but is not stereoselective, resulting in a mixture of syn and anti-addition products. There is another reaction we can use to hydrate an alkene that produces an alcohol with the opposite anti-Markovnikov regiochemistry, hydroboration oxidation. This reaction involves the addition of a hydrogen atom and a hydroxyl group, H and OH, across the double bond, but unlike oxymercuration, the hydroxyl group is added to the less substituted carbon, and the hydrogen is added to the more substituted carbon, following anti-Markovnikov selectivity. Additionally, this reaction is stereoselective, as the hydrogen and hydroxyl group are added to the same face of the double bond, resulting in a syn addition, We get this stereoselectivity as a consequence of the concerted nature of the hydroboration step, where both groups are added in a single step. The hydroboration oxidation reaction begins with the reaction of an alkene with borane, BH3, in tetrahydrofuran, THF, a solvent that stabilizes the borane. This step, known as hydroboration, is followed by an oxidation step, where the resulting organoborane intermediate is treated with hydrogen peroxide, H2O2, and sodium hydroxide, NaOH. Together, these steps yield an alcohol with anti-Markovnikov regiochemistry and syn stereoselectivity. Let's break down each of these steps in the reaction mechanism of hydroboration oxidation. Borane, BH3, is a trigonal planar molecule with 6 valence electrons and an empty p orbital, making it electron deficient and highly reactive. In its isolated state, borane is in equilibrium with diborane, B2H6, a dimer where an electron pair from a BH bond partially satisfies the octet rule for each boron atom through 3-center 2-electron bonding. In the first step of the hydroboration reaction, borane readily forms adducts by accepting lone pair electrons from ether solvents like tetrahydrofuran, THF. This interaction stabilizes the borane, creating a BH3 THF complex that is more manageable to work with. Both diborane and these borane THF adducts serve as equivalent sources of borane for the purposes of the hydroboration reaction, providing the necessary BH3 for the addition to the alkene. In this reaction, each equivalent of BH3 can perform up to 3 hydroboration reactions, and subsequent oxidation in the next step can make the 3 alcohols with anti-Markovnikov regiochemistry. It's important to keep this in mind, but we will be drawing the mechanism of hydroboration to a single alkene. The mechanism begins with the syn addition of boron and hydrogen across the double bond. This reaction proceeds through a concerted transition state where bond breaking and bond forming events occur simultaneously, avoiding the formation of a carbocation intermediate. In this transition state, hydrogen, being more electronegative than boron, bears a partial negative charge, delta minus, and exhibits hydride character. This character allows the hydrogen to align with the carbon that can best stabilize a partial positive charge, delta plus, which is the more substituted carbon. As a result, the boron atom adds to the less substituted carbon, following anti-Markovnikov regioselectivity. This concerted process ensures that the boron and hydrogen are added to the same face of the double bond, resulting in syn addition. The oxidation in the second step of hydroboration oxidation is a multi-step process that transforms the organoborane intermediate into the final alcohol product. First, hydrogen peroxide is deprotonated by the hydroxide anion, forming the more nucleophilic hydroperoxide anion, HO2- and water. The hydroperoxide anion then attacks the boron atom in the organoborane intermediate in a Lewis acid-base reaction, resulting in the formation of a boron peroxide complex. This complex undergoes a rearrangement where the carbon-boron bond is replaced by a carbon-oxygen bond. During this process, the oxygen-oxygen bond within the peroxide group is cleaved, releasing hydroxide into the solution. This step creates a new boron-oxygen bond while converting the carbon-boron bond into a carbon-oxygen bond. In the final step, the newly formed boron-oxygen bond is hydrolyzed by hydroxide in another Lewis acid-base reaction. The hydroxide attacks the boron atom, leading to the release of the alkoxide intermediate. This alkoxide is then protonated by water, yielding the alcohol product. The result is an alcohol with anti-Markovnikov regiochemistry, where the hydroxyl group is attached to the less substituted carbon of the former alkene. Continuing our discussion of alcohol synthesis, let's move on to the synthesis of syn and trans-vicinal diols. In a previous video, we observed that the ring opening of epoxides using either aqueous acid hydronium ion or catalytic base in water, hydroxide, depending on the reaction conditions, produces a trans-vicinal diol. This stereochemical outcome arises from the anti-addition mechanism of the nucleophilic attack, where the hydroxyl groups are placed on opposite faces of the original plane of the epoxide. We've also previewed how to synthesize epoxides from alkenes using peracids, RCO3H, such as metachloroperoxybenzoic acid, MCPBA, conducted in an inert solvent such as dichloromethane. This reaction allows for the conversion of alkenes into the epoxide intermediates, necessary for the formation of transvicinal diols through subsequent ring opening reactions. Let's break down the mechanism of epoxide formation via treatment with a peracid, RCO3H, as part of our broader discussion on the synthesis of transvicinal diols. One commonly used peracid is metachloroperoxybenzoic acid, MCPBA, which consists of a carbonyl group attached to a benzene ring with a chlorine atom in the meta position relative to the carbonyl. This reagent is often represented interchangeably as RCO3H in synthetic steps, where the CO3H group is the reactive business end of the molecule. The term peracid arises from its structural similarity to peroxides, as both contain an oxygen-oxygen bond, which is key to their reactivity. The CO3H group is highly reactive due to this bond and capable of transferring an oxygen atom during epoxidation. Additionally, the acidic proton on the CO3H group contributes to its name and influences the molecule's overall reactivity. This combination of features makes MCPBA and similar peracids powerful oxidizing agents, capable of forming epoxides in a concerted reaction mechanism. This reaction begins with the pi electrons of the alkene attacking the electrophilic terminal oxygen atom of the peracid RCO3H, which initiates the formation of the epoxide. At the same time, the weak oxygen-oxygen bond in the peracid breaks, allowing the transfer of oxygen to the alkene. Simultaneously, the peracid's carbonyl group rearranges to stabilize the molecule. The CO pi bond shifts to accommodate the breaking OO bond, and a proton from the hydroxyl group of the peracid is transferred internally to form the byproduct, a carboxylic acid, RCO2H. This entire process occurs in a concerted mechanism, meaning all bond breaking and bond forming events happen simultaneously, without intermediates. The result is the formation of the epoxide and the carboxylic acid byproduct. Epoxidation is stereospecific, meaning the configuration of the substituents around the carbon-carbon double bond of the alkene is always preserved in the resulting epoxide. For example, if the alkene has a cis configuration, the epoxide formed will retain the cis relationship between the substituents. Similarly, a transalkene will yield an epoxide with trans substituents. This stereospecificity arises from the concerted nature of the reaction, where both new CO bonds are formed simultaneously, maintaining the relative spatial arrangement of the substituents. Recall that epoxides can also be made from halohydrins. We will discuss the formation of halohydrins from alkenes shortly. Now that we've discussed the synthesis of a transvicinal diol from an alkene, let's move on to a new reaction, the stereoselective syn dihydroxylation of an alkene, which produces a syn-vicinal diol. This reaction introduces hydroxyl groups to the same face of the double bond, making it both stereoselective and useful for synthesizing syn-diols with high control over the stereochemistry of the product. We can accomplish this transformation by treating an alkene with osmium tetroxide and hydrogen peroxide to yield the syn-vicinal diol product. Let's discuss this mechanism in detail. The dihydroxylation of an alkene using osmium tetroxide, OSO4, and hydrogen peroxide, H2O2, proceeds via a stereospecific syn addition mechanism. The reaction begins with the alkene reacting with OSO4. The pi electrons of the alkene attack one of the electrophilic oxygen atoms of OSO4, while the pi electrons of the osmium-oxygen double bond are transferred to the osmium. This triggers a subsequent attack on the other carbon of the former alkene by a different osmium-oxygen double bond. The result is the formation of a cyclic osmate ester, where the osmium atom is bonded to both carbons of the former double bond via single bonds, with two oxygen atoms also bonded to the osmium. In the next step, hydrogen peroxide, H2O2, serves as an oxidizing agent, regenerating OSO4 and facilitating the hydrolysis of the osmate ester. H2O2 oxidizes the osmium, increasing its oxidation state and enabling the cleavage of the osmate ester. During hydrolysis, one of the oxygen atoms of hydrogen peroxide acts as a nucleophile, attacking the electrophilic osmium atom and breaking an osmium-oxygen single bond. The sigma bonding electrons from this bond are transferred to deprotonate the oxygen atom that performed the nucleophilic attack. Simultaneously, a non-bonding pair of electrons on the osmium atom moves to form a pi bond with the newly attached oxygen atom. The oxygen-oxygen bond of the peroxide is subsequently cleaved, releasing hydroxide as a leaving group. While hydroxide is typically a poor leaving group, the inherent weakness of heteroatom bonds facilitates its removal in this reaction. The hydroxide ion that was expelled then attacks the osmium atom, breaking the remaining osmium-oxygen single bond and releasing the alkoxide ion as a leaving group. This alkoxide ion is subsequently protonated by the hydroxyl group still bonded to the osmium. The electrons from the oxygen-hydrogen bond of this hydroxyl group are then used to form a pi bond with the osmium, regenerating osmium tetroxide and completing the reaction. The final product is the syn-vicinal diol, where the hydroxyl groups are added to the same face of the former alkene. As we discussed, this reaction is stereoselective for the syn-vicinal diol product and can also be stereospecific depending on the starting alkene. For instance, when the starting alkene is a symmetrical cis-alkene, treatment with osmium tetroxide and hydrogen peroxide produces an achiral product due to the symmetry of the molecule. Conversely, if the starting alkene is a symmetrical transalkene, the reaction yields an equimolar mixture of enantiomers as the syn addition creates chiral products. We've now completed our discussion of all the reactions that convert alkenes into alcohols and diols. Let's move on to discuss the halogenation of alkenes and halohydrin formation. Alkenes undergo halogenation when treated with Cl2, Br2, or less commonly I2, resulting in the formation of vicinal dihalides. These reactions are stereoselective, favoring the formation of anti-addition products due to the mechanism of the reaction. Let's break down this mechanism step by step. The mechanism of halogenation begins with an alkene reacting with a halogen molecule, such as Br2 or Cl2, which we will refer to generally as X2. The pi electrons of the alkene attack one of the halogen atoms, forming a covalent bond between the halogen and one of the carbons in the double bond. Simultaneously, the bond between the two halogen atoms breaks heterolytically, and the newly bonded halogen atom interacts with the second carbon of the alkene, resulting in the formation of a positively charged, three-membered halonium ion intermediate. In this intermediate, the halogen is covalently bonded to both carbons of the former double bond, creating a strained cyclic structure. Next, the halonium ion is attacked by the free halide ion, which acts as a nucleophile. This attack occurs on one of the carbons of the halonium ion from the side opposite the halogen bridge due to steric hindrance and electronic repulsion. This backside attack opens the three-membered ring and relieves its strain, resulting in the formation of a vicinal dihalide. The anti-stereochemistry of the product arises because the nucleophile approaches from the opposite face of the halogen bridge, ensuring the halogens are added to opposite sides of the former double bond. The overall result is the anti-addition of two halogen atoms across the double bond, yielding a vicinal dihalide. The stereochemical outcome depends on the geometry of the starting alkene. A cis-alkene produces a pair of enantiomers, while a transalkene forms a mesocompound. Now let's discuss halohydrin and haloether synthesis. Both reactions follow a similar mechanism to halogenation. The reaction begins with the pi electrons of the alkene attacking the electrophilic halogen atom in the X2 molecule, resulting in the formation of a halonium ion intermediate. Halohydrins are organic compounds containing both a hydroxyl group, OH, and a halogen atom, X, on adjacent carbon atoms. Their synthesis occurs when a halogen molecule, X2, reacts with the alkene in the presence of water as the solvent. Haloethers, on the other hand, are compounds containing a halogen atom, X, and an ether group, OR, on adjacent carbons. These are formed when the reaction is carried out in the presence of an alcohol, ROH, instead of water. Both reactions are variations of the halogenation mechanism and are valuable methods for functionalizing alkenes. Halohydrin synthesis introduces both halogen and hydroxyl groups, while haloether synthesis incorporates a halogen and an ether group, expanding the utility of these reactions in organic synthesis. Here is the mechanism for halohydrin and haloether formation. Both reactions begin with the alkene reacting with a halogen molecule, X2, leading to the formation of a halonium ion intermediate. In the next step, water for halohydrins, or an alcohol for haloethers, acts as the nucleophile, attacking the more substituted carbon of the halonium ion. This regioselectivity results in the formation of the carbon-oxygen bond at the more substituted carbon following Markovnikov regiochemistry. The nucleophilic attack occurs from the side opposite the halogen bridge, breaking the three-membered halonium ring and ensuring anti-stereoselectivity. As a result, the halogen and the hydroxyl OH or ether OR group are added to opposite faces of the former double bond. This combination of Markovnikov regioselectivity and anti-stereoselectivity is a defining feature of both halohydrin and haloether formation. Now we have gone over every alkene reaction that proceeds through the three-membered ring pathway. We only have a few more reactions to cover, starting with hydrogenation of alkenes. Not to be confused with hydroxylation and hydration, hydrogenation involves the addition of molecular hydrogen, H2, across the double bond of an alkene, reducing it to an alkane. This reaction requires the use of a catalyst, such as palladium on carbon, PDC, or platinum, PT, to facilitate the breaking of the HH bond and the subsequent addition of hydrogen atoms to the alkene. The reaction typically occurs on the surface of the catalyst, and depending on the catalyst used, it can lead to predominantly syn addition of hydrogen atoms to the same face of the alkene. However, some catalysts are not stereospecific and may result in a mixture of syn and anti-addition products. Namely, palladium on carbon, PDC, and platinum, PT, as catalysts can result in a mixture of both syn and anti-addition products. This lack of strict stereoselectivity can pose a challenge when a highly stereoselective product is desired, making catalyst choice a critical factor in hydrogenation reactions. To achieve exclusively syn products, Wilkinson's catalyst, ClRH PPH33, can be employed. This catalyst facilitates the addition of both hydrogen atoms to the same face of the alkene through a highly stereoselective mechanism, resulting in only the syn hydrogenation product. This makes Wilkinson's catalyst an excellent choice for reactions where precise stereochemistry is essential. The third to last set of reactions we will cover are cyclopropanation reactions. Alkenes can react with carbenes to form cyclopropanes. These reactions proceed through a concerted transition state, resulting in syn addition products similar to epoxidation, but the three-membered ring in this case does not contain oxygen. Cyclopropanation of alkenes is also stereospecific, meaning the stereochemistry of the starting alkene is conserved in the product. Groups that are cis to each other on the alkene remain cis in the cyclopropane ring, and groups that are trans to each other remain trans. For example, the alkenes cis-2-butene and trans-2-butene, which are stereoisomers differing only in the configuration around the double bond, form cyclopropanes with corresponding cis and trans relationships between substituents on the ring. The cyclopropanation product of the transalkene leads to a racemic mixture of enantiomers, as the trans geometry allows for the formation of two non-superimposable mirror images. In contrast, the cyclopropanation of the cis-alkene results in a single mesocompound, as the symmetrical addition across the cis double bond produces a molecule that is superimposable on its mirror image. We can achieve this transformation by starting with an alkene and reacting it with diiodomethane, CH2I2, and zinc cuprate, ZnCq. In the mechanism, the zinc atom inserts itself into one of the carbon-iodine bonds of diiodomethane, forming a zinc carbanoid species. This step is analogous to the insertion of magnesium into a carbon-halogen bond during Grignard reagent formation. The nucleophilic pi electrons of the alkene then attack the carbon atom of the zinc carbanoid, causing one iodide to leave as a leaving group. Simultaneously, the bonding electrons of the carbon-zinc bond form a new bond with the other carbon of the alkene. This concerted mechanism results in the formation of a cyclopropanation product and zinc iodide as a byproduct. This reaction is stereospecific, preserving the stereochemistry of the starting alkene in the resulting cyclopropane. In addition to the reaction we covered, there are two more cyclopropanation reactions that place halogens on the cyclopropane ring. These reactions involve carbenes, or carbanoid intermediates, containing halogen substituents, providing valuable pathways for synthesizing halogen-functionalized cyclopropanes. For example, treating an alkene with chloroform, HCCl3, or bromoform, HCBr3, in the presence of potassium tert-butoxide as a strong base in tert-butanol produces the corresponding cyclopropane products. This reaction forms a dihalocyclopropane, where two halogens are attached to one carbon of the cyclopropane ring. This transformation is both highly stereoselective for syn addition and stereospecific, meaning the stereochemistry of the starting alkene is preserved. A cis-alkene yields a cyclopropane where substituents on the ring are cis, while a transalkene produces a cyclopropane with trans substituents. We will not look into the mechanisms of these reactions in this video. The second to last reaction we will cover is ozonolysis, also known as the oxidative cleavage of alkenes. This reaction cleaves a carbon-carbon double bond, breaking the alkene into two separate fragments. Each carbon of the double bond is oxidized to form a carbonyl group, such as an aldehyde, ketone, or carboxylic acid, depending on the reaction conditions and the substituents on the alkene. This reaction leverages ozone's properties as a strong and aggressive oxidant to cleave the carbon-carbon double bond, forming an ozonide intermediate in the process. The ozonide is a three-membered ring structure containing two oxygen atoms and one carbon atom, making it highly reactive and unstable. In the second step, the ozonide is reduced using reagents such as hydrogen gas, H2, with a platinum catalyst, zinc, Zn, with acetic acid, or dimethyl sulfide, DMS. This reduction step breaks the ozonide into two carbonyl compounds, aldehydes or ketones, corresponding to the two carbons originally part of the double bond. This two-step process allows for the controlled cleavage of alkenes into their oxidized fragments, which can be valuable for structural determination or synthetic applications. Let's discuss the mechanism of this reaction. For the purposes of this video and the course, we will be using dimethyl sulfide as our reducing agent in the second step. In the first step of ozonolysis, the pi electrons of the alkene attack one of the terminal double-bonded oxygen atoms in ozone, O3, transferring the pi electrons from the oxygen-oxygen bond to the central oxygen atom. Simultaneously, a non-bonding electron pair from the other terminal oxygen atom forms a bond with the second carbon of the alkene. This concerted reaction forms an unstable intermediate known as a molozonide, which rapidly rearranges into the more stable ozonide intermediate through bond rearrangements. In the second step, the ozonide reacts with dimethyl sulfide, DMS, as a reducing agent. The sulfur atom in DMS acts as a nucleophile, attacking one of the oxygen atoms in the ozonide ring and breaking the weak oxygen-oxygen heteroatom bond. The resulting pair of non-bonding electrons on the now free oxygen pushes down to form a carbon-oxygen pi bond, while the carbon-oxygen bond on the adjacent carbon is cleaved, allowing its electrons to form another carbon-oxygen pi bond. This process releases dimethyl sulfoxide, DMSO, as a byproduct and generates two carbonyl compounds. In this reaction, the reducing agent, dimethyl sulfide, is oxidized to form dimethyl sulfoxide, while the ozonide intermediate is reduced, yielding the two carbonyl compounds as the final products. This illustrates the dual redox nature of the process, where the alkene is cleaved and functionalized in a controlled manner. When a linear alkene undergoes ozonolysis, the reaction yields two separate carbonyl-containing molecules. The nature of these products depends on the structure of the starting alkene. If the alkene is symmetrical, the reaction produces two identical carbonyl compounds, as the cleavage occurs symmetrically across the double bond. In the case of a terminal alkene, one of the products is formaldehyde, since the terminal carbon is bonded only to hydrogens. For an internal alkene, the reaction results in two distinct carbonyl compounds, as both carbons of the double bond are bonded to other carbon atoms, excluding the possibility of formaldehyde formation. For cyclic alkenes, ozonolysis produces a single molecule containing two carbonyl groups, typically on adjacent carbons, since the ring structure remains intact and the double bond is cleaved within the cyclic framework. These predictable outcomes are useful in retrosynthesis, as they can help deduce the structure of the original alkene. For example, the presence of formaldehyde in the products indicates a terminal alkene, while two distinct carbonyl compounds suggest an internal alkene. A single molecule with two carbonyl groups points to a cyclic alkene. The final reaction we will cover in this video is the free radical addition of HBr to alkenes. As we've discussed previously, alkenes typically react with HBr to yield products of Markovnikov addition, where the bromine attaches to the more substituted carbon of the alkene and the hydrogen attaches to the less substituted carbon. However, when the same reaction is performed in the presence of peroxides and heat or light, the product follows anti-Markovnikov regiochemistry, with bromine attaching to the less substituted carbon and hydrogen to the more substituted carbon. Furthermore, this reaction produces a mixture of syn and anti-addition products, as it is not stereoselective. This shift in regiochemistry occurs because the reaction proceeds via a free radical chain mechanism initiated by the homolytic cleavage of the peroxide bonds under heat, or light. This step generates peroxyl radicals, which subsequently react with HBr, producing an alcohol and a bromine radical. The bromine radical then reacts with the alkene in the propagation step, forming a new carbon-bromine bond on the less substituted carbon and leaving a radical on the more substituted carbon. This regiochemistry arises from the relative stability of the radical intermediate, as more substituted carbon radicals are more stable, concepts we've covered in previous videos. The addition of bromine is not stereoselective because the bromine radical can attack either face of the alkene, resulting in a mixture of syn and anti products. This reaction highlights the versatility of radical mechanisms in altering both regiochemistry and stereochemistry compared to the typical ionic addition of HBr. As always, thank you for watching, and I'll see you next time.